It's my great pleasure to present the paper Innovation, Automation and Inequality, Policy Challenges in the Race Against the Machine, which was written together with Holger Strulik, who is at the University of Göttingen. The motivation for this paper is that there is a common assumption in growth economics, and that is that technological progress is labor augmenting. So the stock of technologies, typically denoted by A, multiplies with the number of workers, L, in the production function. And that means that as technologies progress and the stock of technologies grows, so as AT grows, the marginal product of labor increases, and that means workers become more productive and they earn higher wages. And in the general models, this typically benefits everybody. So technological progress lifts all the boats. However, in reality, we have the situation that only some workers typically benefit from technological progress, and others might even become redundant. For example, think about industrial robots. The assembly line workers that are replaced, they do not benefit from technological change, but the engineers who maintain the robots or the managers of the firm, they might benefit from this technological progress. Perhaps one of the main reasons why this is not considered in standard economic growth models is that automation as such that is really able to replace workers fully is a rather new phenomenon. So here in this chart, we see the number of worldwide operative industrial robots from 1970 to 2020, according to the data of the International Federation of Robotics. And what we see is that throughout the 1970s and most of the 1980s, the stock of industrial robots was negligibly small, actually. Then sluggish growth set in over the next 2 decades, actually, until the global financial crisis. And when we reached about 1 million operative industrial robots, but only afterwards, so basically in the last decade, there was a takeoff and we observed growth rates at the order of 15% per year in the stock of operative industrial robots. Now, if we want to roughly translate this into how many workers can be substituted by robots, then we can take estimates how many workers can be replaced by one robot, and these estimates typically range between 3 and 6 workers, and multiply it with the number of industrial robots that we have available. Now in 2020, that's 4 million. So we would get to about 12 to 24 million workers that can be replaced by robots worldwide. Now that might sound a lot, but actually compared to the global workforce, which is 3 billion people, that's still quite small. And therefore, arguably, we are still in the infancy of the development of automation as such. And it is, of course, more pronounced in some richer countries that employ more robots per workers than it is in other poorer countries where fewer robots per workers are employed. Now, what we want to do in our contribution is to integrate this automation and the notion that technological progress only benefits part of the workers into the standard R&D-based economic growth theory. Now, this standard R&D-based economic growth theory was very successful to explain how technological progress comes about and how it leads to an increasing GDP and overall higher labor income, particularly in the past, before we had this full automation. However, there are some stylized facts that these models cannot capture. For example, higher incomes mainly went to skilled workers, while there have been stagnating wages of low-skilled workers, particularly in the United States, where the low-skilled workers' incomes or wages have even declined in real terms over the last decades. So by implication, this means that we observe an increasing skill premium and rising income and wage inequality between different skill groups. And this stylized fact cannot be explained by the standard R&D-based growth theory. The third point here is a declining labor income share that we observe since the 1980s, roughly. And before that, the labor income share was actually quite constant over longest periods of human history, which was actually even a stylized fact that economic growth models were deemed to be they should be able to explain this stylized fact of a constant labor income share. However, since the 1980s, the labor income share has decreased, and we want to capture this stylized fact with our model as well. Then we have observed rising wealth inequality or wealth concentration among the rich. So the share of wealth held by rich households has increased over time. And finally, what we also observe in reality and what the standard models do not capture is that there is an increasing share of the population that obtains a college degree. And perhaps the reason for that is that they want to escape the fate of low-skilled workers, of their stagnating incomes, in order to have growing incomes as well, and therefore in order to participate in the gains from technological progress in automation. So our aim is to build a research and development based growth model that includes automation and explains all of these stylized facts 1 to 5 within one framework. So what is our contribution to the literature? Recently, there have been 2 other published papers related to automation, one by Acemoglu and Restrepo in 2018 in the American Economic Review, and one by Emu and Olson in 2022 in the American Economic Journal Macroeconomics. Now, what these papers assume is that new goods, intermediate goods in case of Emu and Olson, or new tasks in case of Acemoglu and Restrepo, are generated by innovation, and they always start out as non-automated. And only in the second step, firms make an effort to automate these tasks or goods, and that means that innovation is kind of a 2-stage process where you always have a share of goods or tasks that are produced by humans. And that also implies that new innovation is never related to automation as such. What we do is we assume that innovation is directly related to automation, and that is consistent with empirical evidence by Mann and Büttmann, published in 2021 in the Review of Economics and Statistics, that the share of patents that are related to automation has increased tremendously over the last decades. So that's a crucial difference in terms of assumptions to these papers, but there are 2 other differences in terms of the content or the focus, where we actually consider endogenous education or endogenous skill upgrading as a way to cope with automation, where people who are low skilled and kind of face wage stagnation, they observe the high skilled people that have increasing wages and therefore can decide endogenously to upgrade their skills and obtain a college degree in order to also benefit from automation. And we believe that this endogenous education response is one of the most important channels to consider as a reaction to automation. And third, we focus in our paper actually more on redistribution policies and their effects. So we look at the effects of subsidies for the poor later on, or subsidies for education, and the implications of a robot tax. So after having sketched out the main motivation and the contribution to the literature, we go more into the details. And first of all, we present the main assumptions and the main structure of the model economy, where we assume that we have an overlapping generation structure where individuals live for 3 time periods. The first is youth. In youth, no economic decisions are made. Young people get basic education in terms of compulsory schooling from their parents or the government, and they also get consumption, so they don't need to decide anything in this phase. In the second phase, that's the phase where all the main decisions are made. That's the working age, when people decide how much they supply of their time on the labor market and how much time or whether they spend some time on skill upgrading, so on obtaining a college degree. And the second decision is how much of their income that they earn to consume and how much to save for the third phase in the life cycle, retirement. So in retirement, they don't have an income and have to live out of the savings from the previous period, as in standard overlapping generations models. Depending on the decisions made in the working age, we then have 3 production factors. The first is L types of workers. These are the workers that chose not to obtain a college degree. They are low skilled, they remain low skilled without higher education. They are better substitutes to machines than the other types of workers, perform rather routine tasks, are therefore easy to automate, and in the structure of our model, they work in goods production. So they are the assembly line workers that are basically replaced by robots. Then the second type of workers are the H types. These are the people who chose to upgrade their skills, who chose to obtain a college degree. They are high skilled. They are more complements to machines than L types of workers. So the tasks that they perform are difficult to automate. And again, in the context of our model, these are the engineers that maintain the robots or supervise the robots in the production sector, or the scientists in the research and development sector that develop the new blueprints for machines and robots. And third, of course, we have physical capital in the form of the machines and robots that are either better substitutes to L types of workers or more complements to H types of workers. Let's come to the consumption side of the model and the specification of the utility function. Here we assume that utility of type J, so this is either low-skilled or high-skilled individual, depends positively on consumption in the second period of life, so when people are in their working age. That's in a concave manner according to a logarithmic utility function. And it depends positively on consumption in the third period of life when people are retired. And that's then savings carried over from the second phase of life, multiplied by the interest rate, where we assume here open economies and the global given interest rate R bar. That just makes it easier to solve for transitional dynamics. It has this abstraction from feedback effects between capital accumulation and interest rates, has no effect on the standard results of the model, but the transitional dynamics would become more complicated if we assume an endogenous interest rate. And then this utility from the third period of life, from retirement, is discounted with the discount factor beta that is smaller than 1 and measures impatience of households. So far, the utility function is almost completely standard as in an overlapping generations model, but now we have an additional term here that refers to the education decision. And this additional term, nu of A, is a disutility of effort if a person chooses to obtain a college degree. And this utility, this negative effect here, depends on ability of the person. So ability is normally distributed in the population. So there are people with higher abilities and people with lower abilities. You can think of it, for example, in terms of the IQ. And if people have lower abilities, they have to exert more effort in order to obtain a college degree than people with higher abilities. And that's what this term captures, the disutility of effort. And then we have the budget constraint that again has a standard conventional part. That's that consumption and savings together must not exceed wage income in the second period of life. But now we introduce a wage tax, tau W, that we use later on to simulate redistributions. And then we introduce the opportunity costs of skill upgrading or of higher education. And that's the second cost of education that we have in the model. Namely, that in the second period of life, people who choose to obtain a college degree have to sacrifice a fraction eta of their available time in order to study for the college degree, and therefore they only have 1 minus eta available for labor supply on the labor market, which means that their income is reduced because they can work only fewer hours in the second phase of life. And then we have a redistribution term, TJ, so that are transfers basically to households, and we make them in general again type dependent. So it could be that the transfers only go to the low skilled workers. That's then kind of something like a conditional basic income, conditional on being low skilled or conditional on having lower incomes. It could, however, also be a subsidy for high skilled workers that would then be an education subsidy. And in general, it also could be not dependent on the state whatsoever. Then it would be an unconditional basic income. Well, and from this setup, the solution for consumption and savings follows in a standard manner. Consumption increases with income, savings increases with income, but consumption decreases with the discount factor, because if people become more patient, they consume less in the second period of life and therefore more in the third period of life. And that's what we see here. So savings would increase with the discount factor better. And then we have the education decision that households also make. And here we assume that households basically compare at the beginning of the second period of their life which decision leads to a higher life cycle utility or rest of the life cycle utility. The decision to obtain a college degree or the decision to not obtain a college degree. And that pins down to the comparison between the disutility of effort to obtain a college degree and the skill premium in terms of utility that you can get when you obtain a college degree and use the higher income for consumption. So here we have the ratio of income of skilled people and unskilled people. So that's the skill premium in terms of income. And here we translate it into utility, so it's a logarithmic utility function, and we have that this additional consumption leads to higher utility in the second period of life and in the third period of life, and in the third period of life, of course, it's discounted with the discount factor beta. So that's the skill premium in terms of utility. If it is higher than the effort, the disutility of effort, then people choose to obtain a college degree, and if it is lower, then they choose not to obtain a college degree. And we denote this by WT tilde, this skill premium in terms of utility. And then we can show graphically what happens in such an economy. So if the skill premium is 0, so high skilled workers and low skilled workers earn the same, then nobody would obtain a college degree because of the effort, the disutility of effort. So the whole fraction of the population would stay uneducated. Now, as the skill premium increases, a greater and greater fraction of the population finds it optimal to obtain a college degree, and therefore the share of people with a college degree would increase, and that's kind of this difference here. So if we are at W tilde here, a share 1 minus AT star of the population would obtain a college degree, and the share AT star of the population does not obtain a college degree. And as the skill premium rises further, the share of the population that obtains a college degree also rises further. What we assume, in our opinion realistically, is that there is a certain threshold value of ability, and if you have ability below this threshold level, you are not able to obtain a college degree and you have to remain unskilled. And this is basically the reason why this function here approaches a bowl. So even as the skill premium increases and increases, we can only converge to a fraction of 1 minus A bar of the population obtaining a college degree, and the fraction A bar would even in the long run and for an increasing skill premium choose to remain unskilled, because the effort that they have to obtain to get a college degree is just so high. After having presented the consumption side of the economy, we now come to the production side. And here we assume that final output is produced with two types of workers. The low-skilled workers with an output elasticity alpha are better substitutes for robots, xi, also with an output elasticity of alpha, than the high-skilled workers that have an output elasticity of 1 minus alpha. The high-skilled workers are the engineers that are complements to robots, and the low-skilled workers are the assembly line workers that are substituted by robots. Now, there is not only one robot variety I, there are as many different varieties as we had technological innovations in the past. So we have the sum from innovation 1, that's the first robot that has been introduced, up to AT, which is the state of technology at time t. So the main difference to the standard R&D-based growth models is the presence of these different types of workers, where the high-skilled workers are more complementary to machines than the low-skilled workers. And then we can compute the factor rewards. For high-skilled workers, the engineers, it's rather straightforward. It's the derivative of the production function with respect to high-skilled labor, and we have the standard result here that wages increase with technological progress. So as AT increases, the varieties of robots increases, and this term here increases, and that raises the marginal product of high-skilled workers and therefore high-skilled wages. We can reformulate this in terms of output, and then we see that as output grows, we would also have growing wages for high-skilled workers. Now this stands in sharp contrast to the wages of low-skilled workers, which are the derivative of the production function with respect to LLT. We see here that this derivative does not involve technologies or overall output. So if the fraction of high-skilled to low-skilled workers stays constant, the low-skilled workers would not benefit whatsoever from technological progress or from economic growth. Their wages would just stagnate. However, as long as some low-skilled workers choose to obtain a college degree in the face of this wage stagnation and that they observe growing wages of high-skilled workers, the numerator here would decrease and the denominator here would decrease and the numerator here would increase, and that means that also wages of low-skilled workers would increase for a certain amount of time. And we can show, however, that this increase of low-skilled wages is always lower than the increase of high-skilled wages with technological progress. So the wages of low-skilled workers might grow with technological progress, but less so than the wages of high-skilled workers. And as we will see later on, in the long-run limit, when no additional people can obtain a college degree because of ability constraints, the wages of low-skilled workers would stagnate while the wages of high-skilled workers could still grow. And then we have the inverse demand function for robots. That's the derivative of the production function with respect to xit. That's again standard, except for the part here where we introduce a robot tax that we also use later on to simulate redistribution. Now I don't go into the details of the intermediate goods sector because it's fairly standard. But of course, we need a research and development sector. And also here we follow the standard assumptions of the R&D-based growth theory that the development of new blueprints, that's the difference in the stock of technologies between time t and t+1, depends positively on the number of scientists employed. And that's the second type of work that high-skilled workers can choose. So they can be engineers in the final goods sector or scientists in the research and development sector. The more scientists we have, ceteris paribus, the more new technologies we would accumulate. But it also depends on the productivity of scientists, delta T bar, where we follow the presentation of Jones, 1995, that we have the inherent productivity of the scientists, delta. Then we have intertemporal knowledge spillovers, at to the power of phi, meaning that it becomes easier to develop future blueprints if we develop blueprints today. So for example, it becomes easier to develop the smartphone if we know how to design the standard mobile phone. But the extent of these intertemporal knowledge spillovers is smaller than 1. So it is smaller than in the Roma framework, where you would have a strong scale effect, and by having this phi smaller than 1, you remove the strong scale effect. And then we have stepping on dose externality, also as in Jones, the number of scientists shows up in the denominator to the power of 1 minus lambda, where lambda is an inverse measure of the stepping on dose externality. So the higher lambda is, the less different researchers would step on each other's toes. And with that, we can derive the growth rate of technologies as a function of these of the productivity of researchers, the knowledge spillovers, the stepping on those externalities, and crucially, the number of people who decide to be scientists in the research and development sector. Now, the problem as compared to the standard R&D-based growth literature of Roma and Jones is that we cannot solve explicitly for the number of scientists in the research and development sector because we have a certain circularity. In order to know economic growth and therefore the skill premium in the next period, we would need to know the number of researchers. But the skill premium in the next period, or the skill premium actually would only lead to the decision of how many people become high skilled in the first place. And this circularity prevents us from obtaining an explicit solution for the number of researchers in the R&D sector. So what we need to do is to resort to implicit analysis and to numerical simulations and a recursive solution later on. Finally, we impose labor market clearing, that the number of high-skilled workers, the overall number, are either employed as engineers in the final goods production sector or as scientists in the research and development sector, and the wages of scientists and engineers, they are equal at equilibrium. And that allows us to derive an implicit solution for employment in research and development, LHAT, that we also have here. And from this rather awkward looking expression, it's already clear that we cannot solve explicitly for LHAT. So what we can do is three things. We can obtain analytical results for the steady states, actually, when there is no shift between low-skilled and high-skilled workers anymore, because we have are at this long-run solution with the ability constraints. We can resort to implicit analysis, of course, and we can also do numerical analysis for the transition periods and for redistribution policies by solving the model recursively. And that's now exactly what we do when we start with the analytical solutions that we can get and the propositions that we can derive from that. Now, the first proposition is rather straightforward. It's that we can show that the equilibrium exists and it is unique. So at any time t, the equilibrium employment level in the R&D sector is positive, and the long-run growth rate rises with employment in research and development and all the standard driving forces of the research and development-based growth literature of Romer and Jones, basically. So they have an effect on the growth rate, either in the transition period or in the long run. So we can basically replicate these models with this equilibrium. So that's the first result. More interestingly, perhaps, we can show that technological progress is skill biased. So with technological progress, the high-skilled wages, they rise faster than the low-skilled wages. So inequality increases, wage inequality increases. And in the long run, when we hit this ability constraint, then the wages of low-skilled workers even stagnate, while the wages of high-skilled workers still grow. And this follows immediately from comparing wages of high-skilled workers with wages of low-skilled workers, where we see that wages of high-skilled workers increase with overall output, while wages of low-skilled workers do not, and the wages of low-skilled workers only rise as long as some low-skilled workers choose to obtain a college degree and become high-skilled workers, so that the numerator and denominator here change. But in the long run, there is no change possible anymore because we've hit the ability constraints, and then only the wages of high-skilled workers grow. Now, this proposition is consistent with the experience in the United States over the past decades, for example, as outlined in Acemoglu and Autor 2012, namely that there has been increasing wage inequality and to some extent even wage stagnation for low-skilled workers. Then what we can also show is that the labor income share is declining. It starts out at a higher level than 1 minus alpha, and then it declines towards 1 minus alpha. And the low-skilled labor income share is actually declining towards 0. Now, the reason or the intuition for that is that the low-skilled workers do not benefit from the new machines, from the introduction of new machines. They are rather substitutes for them and compete with them on the labor market. So if new robots enter the economy, the income that they earn is not anymore earned by the low-skilled workers, but instead it's earned by the robots, and therefore by the people who own the robots, and these are the people who own the wealth in the economy and the capital stock. So that means that increasing automation is associated with a decrease in the labor income share, in particular with a decrease in the low-skilled labor income share. Now, this prediction is consistent with empirical findings presented by Elsby and co-authors in 2013 and by Karababunis and Naiman in 2014, that actually since the 1980s, the labor income share is decreasing in many countries of the world. Next, we can show that with economic growth, wealth concentration is rising. For this, we can compute the share of wealth held by high-skilled workers, which is actually the saving rate of high-skilled workers multiplied by high-skilled income, divided by the saving rate of low-skilled workers and high-skilled workers multiplied with their income. So that would be savings of high-skilled workers divided by savings of high-skilled and low-skilled workers. But in our simple setting, the saving rates of high-skilled and low-skilled workers are the same, so they drop out, and it's just the ratio of income of high-skilled workers divided by income of high-skilled and low-skilled workers in the economy. What we see here is that as output in the economy grows, the numerator grows and the first part in the denominator grows, but the second part in the denominator stays constant. And that means that for a growing economy, the share of wealth held by high-skilled workers is gradually increasing and in the long run limit approaching 1. Now, does this change if we assume different saving rates of high-skilled versus low-skilled workers? No, because high-skilled workers with higher incomes would typically have a higher saving rate. So if we relax this assumption that the saving rate of low-skilled and high-skilled workers is the same, this would rather reinforce our result here in this proposition. And this prediction in turn is consistent with the data that Piketty presents in his famous book of 2014 and the data that is presented by Alvarado and co-authors in 2017, that basically the share of wealth held by the rich basically increases and we have growing wealth inequality. Finally, we observe skill upgrading. So with technological progress and growing wages of high-skilled workers, the share of people that obtain a college degree in the population would increase and converge in the long run to 1 minus a bar due to the ability constraints. Now, the reason for this is the race between education and technology. So the low-skilled workers who face wages that do not grow as fast as the wages of high-skilled workers and in the long run might even stagnate, they would try to also benefit from technological progress by upgrading their skills and also obtaining a college degree. And this, of course, might go well for a certain amount of time, but if we have the ability constraints, it means that inevitably in the long run, the race between education and technology would be lost by some people in the economy. Now, overall, the prediction of an increasing share of graduates is consistent with the literature on the race between education and technology, for example, Goldin and Katz 2009 and Acemoglu and Autor 2012. Now, all of the results so far have been obtained analytically, these propositions, and that means, as compared to our slide that we had at the beginning, that we are able, with our automation augmented research and development based growth model, to explain all of the stylized facts that I presented at the beginning. So not only the effect of innovation on GDP and labor income at the aggregate level, but also on labor income inequality, on increasing skill premium, on the declining labor income share, on a rising wealth concentration in the economy, and on this fact that there is an increasing share of people obtaining a college degree in the economy. So all of these aspects our model can explain. To illustrate the transitional dynamics and to be able to analyze transfers and taxes, we now simulate the model numerically. And for that, we normalize the population to 1,000. We assume that the extent of intertemporal knowledge spillover is smaller than 1, so we are in the Jones case, not in the Roma case, where these would be equal to 1. We assume that a generation lasts for 25 years and start the simulation in 1950. We set the worldwide interest rate to 4.5%, which is an average between the rate of return on the stock market and the risk-free rate over that time period. We set alpha equal to 0.6, which would imply a long-run labor share of 0.4. Then eta, which is the time, the fraction of time in the second period of life that one needs to obtain a college degree, is equal to 5 years for a college degree, divided by the time period that one has available in the second period of life, where we assume that labor market entry is at age 19 without a college degree, and retirement at the age of 63, and that leads to eta being equal to 11%. A bar is set arbitrarily to 0.5, but even this arbitrary value leads to a relatively good fit between the model implications and the data. And then we try to fit end of 20th century trajectories for DFB growth, the college share in the population, so the share of the people that have obtained a college degree, and the skill premium of about 90%. And we set all the other parameters in the model such that we achieve this. Simulating the model with these parameters then leads to the following picture, where we have here in the first diagram the share of graduates in the economy, in the second diagram the share of people working in the research and development sector, and in the third diagram the ratio of wages between high-skilled workers and low-skilled workers. The blue solid line is the model prediction, starting at 1950 and ending at 2100. So 1.5 centuries actually we simulate here. And the red dashed line, that's the data. And we see that the share of graduates has increased in the population, and that's also what the model predicts. The model slightly over predicts the increase. With respect to the research and development share of the population, so of the people that work in the research and development sector, that increased from about 1% to 2.5% in the data. And also the model predicts an increase, and also this increase is slightly steeper than in the data. And finally, the skill premium also increased from the 1960s to 2020, and the model also predicts an increase in the skill premium. So the model replicates the data comparatively well. At least everything is kind of in the ballpark, and so we are confident that we can use this model for the policy analysis that we start next. What we do for this policy analysis is to assume that a certain policy, in this case, in the first case, a redistribution to the poor or to the ones who are unskilled, is financed by the different taxes, where we set the robot tax equal to 5%. And we compare this to the situation when we set the wage tax to 10.3%. Why these different tax rates? Because they lead to the same revenues in the year of implementation. Here we assume that the simulation starts again in 1950, and the tax now is introduced in the year 2000, and together with the redistribution, and we have then three trajectories. The basic baseline model simulation that we already know from the previous graph, that's the solid blue line, and then two additional trajectories. The red line refers to the situation when we finance the redistribution with a wage tax, and the green dashed line, the situation when we finance the redistribution with a robot tax. What we see immediately is that with such a redistribution to the poor, the share of graduates during the transition is lower. The reason is clear, because the subsidy for those who remain unskilled is actually a subsidy for not getting educated, and that reduces the share of people obtaining a college degree, which in turn reduces the share of the population working in research and development, and therefore this reduces TFB growth. So we have a sacrifice in terms of economic growth, but in exchange we get a reduction in inequality. So here we have the wages of low-skilled workers, and they would actually stagnate in the long run without the tax transfer scheme. But with the tax transfer scheme, these people also gain and also have increasing incomes, because they get the redistribution from the taxes that are also paid by the high-skilled workers. So the pre-tax income ratio is slightly reduced here, and we get less inequality and have a typical equity efficiency trade-off. So we buy less inequality by also having less efficiency, basically. What's interesting in this context is that if we finance the redistribution with a robot tax, the effects are actually more pronounced. So we get a stronger reduction in growth and a stronger reduction in inequality. The reason is that this robot tax discourages innovation further because it's a tax on these intermediate goods where the new innovations are basically put to use. In a nutshell, one important thing and one important aspect here is that there is a trade-off, so we don't have a magic bullet. So the robot tax is not a magic bullet as it is sometimes presented in the media or in general discussions. It also leads to an equity efficiency trade-off and it would reduce growth. So perhaps it's in the end a policy decision of whether one wants to introduce it or not, but it's not, of course, a free lunch. Now, another policy that is often suggested in the age of automation is actually an education subsidy. So to try to encourage people to obtain a college degree in the realms of our model. And we can do this by now conditioning the transfers to flow to those people who obtained a college degree. So we again use the same tax rates, but now we only subsidize the high-skilled workers in the economy. So uppercase T, J only goes to the H-type individuals in the economy. Now, what we see first when we focus on the solution when this is financed by a wage tax is exactly what we would observe, what we would expect. Namely that the share of graduates during the transition increases. That means that the share of people working in the research and development sector during the transition increases and DFB growth during the transition increases. But in exchange, we get more inequality, particularly after taxes, because the low-skilled people would finance the tax but not benefit from it, and we get even higher inequality. So actually, when we finance it by a wage tax, this redistribution, we get the opposite of what we had previously. We get faster growth during the transition, but higher inequality in exchange. And in addition, we don't get faster growth in the long run. That's important here because at some point we hit the ability constraint. And when we hit the ability constraint, it doesn't help to subsidize education further because it's just not possible for a certain fraction of the population to obtain a college degree. Now, when we finance the redistribution with a robot tax instead, then something surprising, in my opinion, happens, and that is that actually the subsidy on education even leads to a slight reduction in the share of graduates and a reduction in the share of people working in research and development and a reduction in DFB growth. And the reason is that this effect that the robot tax discourages innovation overcompensates even for the effect that we have this education subsidy. So therefore, there is also no increase in inequality with the robot tax. Actually, we would even have a decrease in inequality here. However, again, in general, as we see, it's not a magic bullet, the education subsidy. We face trade-offs and it bends down in the end to a political decision. Up to now, we have assumed that there is no unemployment in the model. And one of the central fears in relation to automation is actually that we will face technological unemployment, widespread unemployment, because robots will do all the work and so on and so forth. And some people might starve and things like that. To analyze this, we extend the framework here by the possibility of unemployment by introducing the fair wage theory of Akerlof and Yellen in order to get an elastic labor supply of households. So far, labor supply of households was inelastic. They would always supply the full amount of labor, even if the wage is very low. And here we introduce elastic labor supply. So households would react if the wages are very low. And the way we introduce it is this Akerlof and Yellen's fair wage theory, where we assume that people exert certain effort at work, and this effort depends on the comparison of the wages that they earn with a reference wage in the economy. And if they perceive their own wage as unfair, they would not exert full effort. So effort is the minimum between 1 and the wage comparison between my own wage and the reference wage. If the reference wage is higher, I reduce my effort below 1. And then we introduce these effort variables here in the final goods production function, effort of high-skilled workers multiplied by high-skilled labor supply and effort of low-skilled workers multiplied by low-skilled labor supply. Now we have to specify how people form their reference wages. And here we assume that the reference wage, here of low-skilled workers and here of high-skilled workers, is a weighted average of the wage of the other group. So in case of low-skilled workers, the wage of high-skilled workers, and in case of high-skilled workers, the wage of low-skilled workers, and one's own market clearing wage that people know. And the weight is given by mu for the other group and 1 minus mu for my own market clearing wage. And then we can plug in the market clearing wages by denoting labor supply of type J by Lj bar. We get high skilled wages by plugging this in, and we have here this AT tilde that depends positively on the stock of technologies. So the wages of high skilled workers increase with technological progress. And here we have the wages of low skilled workers, as we know it previously, depending on the share of high skilled versus low skilled workers. And now, of course, high-skilled workers always receive a wage that they themselves perceive as fair, because the wages of low-skilled workers are lower, and therefore the reference wage of high-skilled workers is always above 1. Therefore, we can focus on the labor market for low-skilled workers, actually, where unemployment would show up. For this, we have two equations, actually, that describe the labor market equilibrium. The first is the inverse demand function for low-skilled labor, given by the expression for wages that we had on the previous slide, depending on the supply of high-skilled and low-skilled workers. And it's important to note that this function is downward sloping in the space of wages and labor supply of low-skilled workers, downward sloping with LL bar. So if we have this graph, here we have labor supply of low-skilled workers, here we have the wages. Then if labor supply is low, wages would be high, and if labor supply is high, wages would be low. So that's the downward sloping inverse demand curve for low-skilled labor. The second expression is a so-called fair wage constraint. That would be the wage rate at which low-skilled workers would perceive their wages fair and exert full effort. And that would be if the wage that they receive is actually mu times the wage of high-skilled workers, plugged in from the previous slide, and 1 minus mu times their own market clearing wage, W. Now this function is, if we take the alpha of 0.6 that we assumed in the numerical part, it's upward sloping, actually. And in any case, for a lower alpha, it would still definitely have a less steep slope than the labor demand curve here. So we would always have an intersection between the two curves, actually, that determines the labor market equilibrium for the case that we have here with fair wage comparisons. In case of the basic model without fair wage comparisons, the labor market would just be described by the vertical labor supply curve here and the downward sloping labor demand curve. And the labor market equilibrium would be here at a lower wage and full employment. And whenever something changes, only the wage would react, employment would not react. Here we now have two margins that can react: labor supply or unemployment as such, because the wage is now higher than the market clearing wage due to the effort constraints, and the wage, of course, itself. So now what we observe is the labor market equilibrium is here. At employment LL0 of low-skilled workers, labor supply of low-skilled workers is LL0 bar, and therefore unemployment is the difference between the two, LL0 bar minus LL0. Now the question is, what happens if there is technological progress? So technological progress means an increase in AT tilde. So we see here immediately this shifts the fair wage constraint upwards, but it has no effect whatsoever on the inverse demand function for low-skilled labor. So this curve here stays the same, but the fair wage constraint shifts upwards. Now, ceteris paribus, if the labor supply of high-skilled workers would not change, this would mean higher unemployment of low-skilled workers. So we would get higher technological unemployment in case of technological progress here. However, a priori, we do not know whether the labor supply of low-skilled workers reacts, because during the transition, some of them could still decide to obtain a college degree and become high-skilled workers, and therefore LL0 bar can shift inwards. And we could, for example, have this labor supply. So a priori, we do not know whether unemployment would increase or decrease with respect to technological progress. And that's interesting because it shows that we can have technological progress that would lead ceteris paribus to technological unemployment, but nevertheless we could observe in the data a reduction in unemployment because of the reaction of endogenous education actually. And that would be one possible explanation for why unemployment has not yet increased in the face of automation. So one possible explanation, for example. So in general, we cannot say whether technological unemployment would increase or decrease with respect to technological progress. But what we can say is that when we hit the ability constraints, then technological progress will always lead to higher unemployment. So we have a proposition for the long run steady state. Once that education has converged towards its upper bound, more innovation and faster economic growth would lead to more involuntary unemployment. Now we can simulate the model again with technological unemployment, and we see most of the things remain as in the baseline simulation. So we again have a robot tax, a wage tax, and this redistribution and equity efficiency trade-off and so on. But what we have is that the unemployment rate becomes an additional margin of adjustment. So it's not only that wages and inequality react, but also unemployment as such reacts. What we also see here is that unemployment remains fairly constant for quite a long period of time, even though we have technological progress. And the reason for that is that the unemployment raising effect of technological progress is compensated, at least to a large extent, by the education fostering effect of technological progress. Only then in the long run, when we hit this ability constraint that the share of graduates does not increase anymore, will also unemployment start to take off and increase faster. And that means that over long periods, actually, we can observe constant unemployment and even decreasing unemployment for certain parameter values. We had this in some of our simulations, even though there is a direct unemployment increasing effect of technological progress. And that might explain to some extent why today in this environment with fast technological progress, huge automation and so on, we still do not observe technological unemployment at a large scale. So we can come to the conclusions now. What we were able to set up is a research and development based growth model for the age of automation that takes industrial robots into account. And this model, in addition to what the standard R&D-based growth literature can explain why there is a declining labor income share, where there is rising income and wealth inequality, why the share of college-educated workers has been increasing over the last decades. And it could also explain how potentially technological progress might lead to technological unemployment, even though we might not see it in the data for quite a substantial amount of time. Overall, the policy conclusions are that there is no kind of magic bullet that we have at our disposal by which we could compensate for some negative effects of technological progress as such, but that they are all political decisions of whether we want to implement them or not. In the end, however, the low ability types would lose the race against the machine, if you want to call it like that. And it's not easy to come up with policies that would benefit them. There are some potential solutions that one could think about. One would be to raise abilities in the first place. So that a greater share of the population can obtain a college degree, for example. That would mean in practice to invest in preschool education, compulsory schooling, education of teachers, and so on and so forth. So that could be one possibility. Another possibility is that we have seen that a robot tax in this context is not something that is desirable because it discourages innovation. So we don't want to tax robots then if this discourages innovation and reduces income growth as such. But there could be other things that are not so desirable. For example, pollution. So we could introduce environmental taxes, for example, on CO2 emissions, because that's a negative externality. So we want actually to reduce it, and couple this tax with a redistribution policy where particularly those benefit that have so low abilities that they cannot obtain a college degree in the first place. So that might be one taxation transfer scheme that could work in reality. Of course, pollution was not in our model and so on and so forth, but this could be something that might do the trick. And finally, what I find quite interesting is a progressive consumption tax. So the consumption tax, of course, the value added tax, has the problem that it is regressive. It does not distort the labor market, that's the positive side, but it is regressive because low income people pay a much larger share of their income on these taxes, because the taxes are a constant fraction of consumption expenditures then. However, it could in principle be made progressive. One proposal would be that at the end of the year, at the moment, we report our income to the tax office, and then what we consumed that can be deducted from the taxes. And on the rest of income, there is a progressive progressive income tax applied in most of the countries. However, it could also be the case that we actually report our income, or the tax office knows our income basically, and we do not report what we consumed that is tax deductible, but we report what we saved actually. And then the rest is consumption, and on this progressive consumption tax is applied. And this would have the additional advantage that there is no incentive anymore to shift wealth into tax havens, because if I don't report the savings to the tax office, that actually increases my consumption and therefore my the taxes that I have to pay. So one would strike two birds with one bullet in this case, and it might be an interesting idea. So overall, I thank you very much for your attention.